Hello, Leah. How are you? Oh, there they are. All right. Are you there? Leah didn't answer. Ben, Daniel, Landon, you guys are all functional. Everybody's ready?
Here, yes, functional, dubious.
I love it. Beautiful answer, Daniel. So you guys are all tracking along in My Open Math as far as notes and grades, etc., just to make sure that everything is cool. Keep an eye on there. You have a retaining wall project that I probably already have from you. It was due a while ago. And then maybe some chapter 3 homework that I need to get in there. So I'm going to work on that when we get out of class today.
Hello.
There's Leah. Awesome. So anyway, keep tabs on that. Make sure you're all good. I do wanted to quickly, how come that stopped sharing? Why did that go away? I do want to quickly do one other question that we didn't get to from chapter 3. And if you do need to change anything in your chapter 3 homework, awesome. And I also warned you, I don't know if you, at the time, you didn't think much of it, but did you see how ridiculously devastating 323 is? Only because you end up with an equation that you can't solve. And I think that's just kind of cool to notice that. Only because like that's weird that that happens in such a kind of a simple question. But anyway, you had a question or two that was kind of like this one that I have up right now, and I wanted to talk about that just quickly before we kind of launch into the next discussion. But I think it's called Hooke's law or Hooke's property or something like that. It's sort of the spring thing, and it really, the best way to understand it is really force divided by distance is constant. Because again, I'd like you to have a conceptual understanding. And again, the spring thing shouldn't be totally new to you. I mean, you may have survived the assignment questions just fine based on whether or not the physics discussions about spring stuck in your head. But the best way to understand Hooke's law is just to say, hey, if you double the force, then it'll double the distance you pull the spring from its kind of resting situation. So just to make sure you have kind of a good understanding of it. If it's, actually, let me draw it this way. If you got some kind of an object here, and then you pull it out to here, what we're talking about is the distance. The distance d is how far you pulled it from wherever rest is. So from kind of its resting position, that's distance d. And so all Hooke's law really says is he noticed, and this is true for quite a few things. I'm actually reading a book about deflection and some of the formulas that you get to in other engineering classes, and it's true for more things than just springs. If you double the amount of weight on something, it'll double the amount of deflects down. And so if you double the force, then you'll double the distance. I mean, that's really all Hooke's law is saying. But one of the things that I think people misunderstand is like, that's the definition of, that constant is the definition of what when in a physics class you call a spring constant. Look at the units. I mean, force, isn't force measured in newtons, and isn't distance measured in meters? So the fact that the spring constant is newtons per meter makes sense. And so to act like a spring just kind of has some magic constant to it is really not, it's not really quite that complicated. If you took a spring and you had a little scale to measure it, and you just pulled it out 0.1 meters and you measured the force on it, divide them, and you just found the spring constant. Like, it's not like you have to look it up in a book somewhere. So I just want to make sure you kind of understand that concept. So that, you know, in the end, the formula that you see, they kind of resolve it like this. It'll say the force is over here by itself, and they'll multiply the d up to this side. So it'll be k times d, where k is the spring. Like, that's what you see in a book. But I'm just saying that's not the best way to understand how simple this concept really is. It's just somebody stretching on a spring and noticing, hey, when I doubled out how hard I pulled, it doubled how far the spring pulled. I mean, that's it. And you write down those two measurements and you found the spring constant. So the fact that it's linear, I guess that isn't obvious. It isn't obvious that it'd be linear if you double it. If you double the height you drop a rock, it doesn't double the time it takes to hit the ground, for instance. That's not linear. That's a squared relationship. So anyway, so anytime you see a spring kind of thrown into something, as I said, especially in 323, it really just adds one more step to the problem. And I just want to quickly do this one. So I probably won't grade you down on your assignment if you did not draw a free body diagram. As I said, sometimes you sort of don't need them because the drawing is already there. But at very least, if you're in lazy mode, as I said on a test, I'm going to make you draw it. I'm even going to put a spot there and tell you it's worth 5 points or whatever. You got to go back to this figure over here and say, well, that point D is being pulled on with 3 different forces. And just as a reminder, because we're going to use this some more today, those are assumed to be tension. See how they're all pulling? They're all pulling equally on D. So those are assumed to be in tension. What do I know? Well, the only thing I know, and I told you this quickly running out the door the other day, but because this is 40 kilograms, metric, remember, that's not a force. Newton is a kilogram meter per second squared. So when I multiply 40 times 9.81, that turns into a force for the first time. 40 times 9.81, I already have that written down. Why did I do it again? I get 392.4 newtons. So mass is not a force. So I have those two. And then I don't know anything about the other two. And so they're just kind of being pulled on in some random way. So since this one is kind of aiming up there toward B, I'm going to call that the force toward B. And the other one's aiming toward C. I'll call it the force toward C. Again, name them, but it doesn't matter how you name them. Call them force 1, force 2. Fine. And then in this particular case, we have the position shown. In other words, we know all of the dimensions. And so because this is a distance of 2 and that's a distance of 3, if I do Pythagorean theorem, this distance would be the square root of 13. This one is 2 and 2, so that'd be the square root of 8. So really what I have over here then is, if I want to include it in this drawing, is kind of the fact that I can tell what direction this is going. For 2 horizontal, no, wrong, 3 horizontal. For 3 horizontal and 2 vertical, my hypotenuse is the square root of 13. So that's how I know what direction that's going, not by an angle. And the same is true for this one over here. It's going 2 and 2, square root of 8. So now I have everything I need to know to establish equilibrium. And so I've got 2 equilibrium equations. I've got the sum of the forces in X that need to be equal to 0. So notice the 39.2 makes no contribution to that, but the other two do. And visually I can see C is going left and B is going right. So I think I'll just use that convention and say force of B modified by 3 divided by square root of 13. So that's the proportion of it that's going horizontal. So that's going right. And then force of C is going left, modified by 2 over the square root of 8. And that's got to add up to 0. Again, I think, darn, 2 unknowns, don't like that. But we're going to come back and make a second equation for the sum of the forces in Y that also need to be 0. And that'll give us our second one. Now they're both pulling up. So again, I'm just assuming from the picture, those are both positive. So I can say the force of B modified by 2 over the square root of 13, that's going up. Force of C is going up, modified by 2 over the square root of 8. And then the one I forgot the other day, that one constant that's going straight down, is down 392.4. That has all got to be equal to 0 for equilibrium as well. So again, I say, cool, 2 equations, 2 unknowns. So I'm just going to save us some time here and say solve the system. That's the math language for a system of equations, 2 equations, 2 unknowns, system of equations. I get that the force in B is 283 newtons, and the force pulling towards C is 333 newtons. So, normally I'd be done. Great. And remember, the main reason you just made this calculation is that you would come back here and say, now I know how strong of a cable to put into this system so it actually doesn't rip in half. But in this problem, they asked us to do something interesting, which is, if you imagine hanging the box onto this, it's going to pull down on it, and that spring's going to allow BD, this black line over here, to elongate. It's going to actually get a little bit longer. So then they asked us about the unstretched length. So its stretched length is the square root of 13, because that's kind of the That's the box, the heavy 290, 392 Newton box pulling down on it. So it's been stretched out. And so, well, now that I know the force on it, I'm just going to go back to this equation right here where I kind of know everything. I know everything that I need to know. I now know how much force is on it. I know. I guess I'll go back here. Yeah, that's fine. So I know how much force is on that. That was force B, so that's 283. And I'm going to throw that in there. And then I knew the spring constant from the beginning. They gave me that that was 180. So all I have to do is divide those and I get D. Well, I get D is 1.57. When I divide those, and I guess that'd be meters because everything else was meters. And great. That's my D. What is D? What is that? What does it even mean? Remember what D tells us? Because D is not the length of the rope. Does that make sense? Remember, D is how far did this thing actually stretch? So this is how much it actually stretched. Has nothing to do with how long the rope is. Does that make sense? Oh, cool. Well, what's the square root of 13? I mean, the actual length, the square root of 13, I'll just move down here. The square root of 13 is approximately 3.606. And that's what it is now. And so if it stretched 1.57, then if I subtract those two, that must be how long it was before it was stretched. Does that make sense? If I subtract those, I get like, what is that, 2.1 approximately? 2.03, something like that. So this is the answer that you would see in the back of the book for that question, because it was asking for how long was it before you put weight on it. So if it's 2.03 and then you put the weight on it and it's stretched according to Hooke's law, another 1.57, then it would make sense that it ended up kind of the square root of 13 long in the end. And so if you stare at that sort of too early, then that can be really confusing. Given that that was, something I wish you would have known before you finished your assignment. I mean, a few of you, tell me where you guys are. Like, are you like, oh yeah, I already knew that from physics. Thanks for the quick reminder, but I already got it. Are you like, oh, okay, great. Now I get that a little better. Maybe I should go finish a couple things on that assignment. I mean, where are you guys at?
I thought I knew it, but I messed it up.
Mm-hmm. Feel free to fix it. And if you want to stay after class and ask me about 323 as an example, like you guys aren't asking me near enough questions. Like we should be talking more outside of class about, maybe you have access to Chegg and you're looking at, solutions so you can reverse engineer and kind of teach yourself how to do this some, but I guess I'm just surprised you're not asking me more questions. When I solved 323, I ended up with a fourth degree equation, like the distance was to the fourth power. And so, wow, surprising. Okay. Well, the good thing is we still really don't have to learn anything new today. As I said, we're in many respects, we're done in this class right now learning new things. We just need to deepen our understanding of them. And on one of the pages in your book, maybe it'll say on here so that I can tell you where this is in your book. No, it does not. Let me see if I wrote it in my notes somewhere. This is a page out of your book, but it's something you're going to need to have on your test. For your test. I don't know, maybe that's not true. But we've been ignoring like everything and I've already mentioned this a little bit, but we've been ignoring how things have been supported. And now it's time to start paying attention to that. So all we're going to do is just add this to the list. And so I posted this page in my open math for you. I think I did. Yeah, I did. But as I said, it's one of the pages in your book. It's just that it's nice to have it, you know, sitting beside you, printed, so to speak, instead of always having to flip it open in your book somewhere. But I'll show you what I mean about this. And what I'm going to focus on is just the few of these that you're going to see all the time. So let's look at the bottom one first, a fixed support. That means it's welded to the wall. It's screwed to the wall, something like that. And what that means is it's able to provide some help. In other words, we've got to get all forces to go to zero, which we did last week. But now we also even got to consider all the moments going to zero. In other words, you can't have this thing sliding up or down, moving left or right, and we can't have it rotating either. And so the cool thing about a fixed support is, would you agree that if it's screwed to the wall in some way, it is providing, well, as they said here, 3 unknowns. In other words, the reaction at that point. If I pull on that, ideally, it's not going to break. And so stare at this picture as I draw on it for a second. In other words, because it's fixed, if I pull in that direction, it's not going to want to go immediately. Now, if I pull harder, eventually it probably will pull out of the wall. But it's providing resistance there. Because it's fixed, it's also providing resistance vertically, like it doesn't want to slide up and down. And because it's fixed, it's even providing kind of a desire to rotate, like it's resisting rotation as well. Does that make sense? That's why they say over here that this has got 3 unknowns. It's actually providing support in all 3 of those ways. And we'll tackle a problem like this right off the bat in just a second. Whereas take a look at, and so that's one of our important ones, a number of your connections that we've been ignoring to this point are fixed. The second to the next one up, notice that is a hinge. Do you see how it says there are only 2 unknowns? So it's pin, smooth pin or hinge. And again, if you look closely at the drawing, you can kind of see that. But this is a super common kind of a support where I don't want that end to move, but I do want, like when the train goes over, I do want it to be able to flex a little bit. Does it make sense? Because it's pin connected, then there's only 2 things it can do, and they're written over here. I mean, it's like it can provide vertical and horizontal support. It's going to not allow the part to lift up. It's not going to allow it to go sideways. But does it make sense? There's nothing preventing rotation there, so it's not going to help with rotation. So we got to start looking at that. So you don't really have to have this sheet in front of you. You just got to stop and think about it. Because what you have to start doing in your free body diagrams is adding these arrows to the picture. You got to add them in yourself. They're not there. They're not just the arrows that are in all of the problems. And the third one you're going to see a lot, even though there are 10 of them here, is this one, the rocker. In other words, it's just sitting there. For instance, did you know this? When you build a bridge over an embankment or over a river or something like that, it's pretty common to actually just set the concrete right on top of a couple of posts so it can move. Why would you do that? That just seems dumb. Why wouldn't you connect it? Why would it just be sitting there? Why wouldn't it be connected? Wouldn't you think they would want to almost like pour one big chunk of concrete that maybe looks something more like this? Wouldn't that be stronger? Why would they want the top just to sit on top of the other one? Take a guess.
Maybe if it didn't allow enough movement, it would like break more often.
Yeah, notice if it's allowed to move, then maybe it won't break. Why would it move though? There's a few reasons. Why would it move?
Because like concrete is not really liking to move. It's not like designed to move. If it's like in one piece, it will crack.
Mhm.
And I don't know about, I think the river, because like you can get big floods and it moves, I guess, a little bit,
Yeah.
the earth
What
around,
could
and it's
cause it?
just,
Earthquake could cause it. If the earthquake starts shaking it, does it make sense if it was fixed like this example up here, then it's going to want to crack. Whereas if it was an earthquake, then this top one could just kind of slide left and right and it wouldn't break. So, I mean, you wouldn't want it to slide all the way off because then it would break. But the earthquake is one of them. Also, you know this, what happens to things when they get warm? Do they just stay the same?
They expand.
They expand. So if you connected that when, as I did up here with kind of a fixed connection in some way, if you welded it together right there, it's going to expand and it's going to break things. And so it's allowing for expansion. So, you know, and even a truck like skidding on it, who knows what might make it move. But this rocker support is also kind of interesting. But notice it's real interesting what support it provides. There's only one unknown for that. And notice, as they showed in this drawing over here, and they said it in this situation, that rocker only supports perpendicular. Does that make sense? In other words, where is the arrow there? It's perpendicular to the surface. It's not horizontal. It's not vertical. And so notice they said over here in the notes, and that's pretty important. The reaction is a force which acts perpendicular to the surface at the point of contact. Like you're going to have to add these arrows in yourself. You're going to have to look at the figure and go, oh, look, they drew in a rocker support this time. And so then you've got to add that arrow yourself. And we're going to actually figure out how much force is at that point. Engineers call that a reaction. So you put this heavy load on the bridge and then there's some kind of a reaction. So there's 10 of them here, and you know, all kind, and we can look those over later, but let's dive in and I'll show you what I mean in kind of this first example. So let's stare at this for a second. Again, as all these problems, there's just kind of random forces on it. There's like a 6 kilonewton force in some location, and then there's a 4 kilonewton force, and we don't have any idea what the heck those are, where they're coming from, and so forth. But notice what's interesting about this is that whole system is cantilevered out over the top. And so, you know, this is an example of something that's maybe lifting a weight away from a wall. But what I want you to understand, or want you to think about, is how does that appear to be connected at the wall over there? What kind of a support is that? Blurt it out. You might be wrong, but blurt it out.
First impression is it looks like a gusset.
Yeah, notice it's not obvious. It doesn't look exactly like what's in the book before. What do you think?
Would it be directly connected to the wall, or would it not be that?
Yeah, it looks like I don't see a pin like it's made to hinge. Does that make sense? And it, you know, appears to be attached with a plate or a gusset, like Landon said. It appears to be a fixed connection, but you know, that takes some practice to see. Now, if you think about it, wouldn't it have to be fixed though? Like if you had a board sitting out here with a whole bunch of weight coming down on it, and you attached it with a pin over here to the wall, does it make sense? Well, then it's just going to get pushed down. Like even under gravity, it's just going to go punk and get pushed down and go nowhere, right? It's just going to, like, that wouldn't make sense. Like you want that to do a job, it's probably connected at the wall with a bunch of screws in it and so forth. So that's a fixed connection, not obvious, but they want us to think that's a fixed connection. Now, did they tell us that in the problem? Because we're not very good at this yet. Yes, they said at the fixed support A, and they said on the cantilevered beam. And so what we've been doing up to this point is just saying, well, let's find all the sum of the forces on this and maybe reduce them to one. Like we have 2 forces here and reduce them to 1. And so we found the single vertical force, the single horizontal force, and the single desire to rotate. But what we're talking about now in chapter 5 is, well, the same thing. It's equilibrium. So we need, though, the sum of everything to be 0. So we need the sum of not just the forces in X and the forces in Y. Notice this is two-dimensional, so I don't need a forces in Z, but we also need the sum of the moments to be 0 as well. In other words, this thing cannot be rotating. The basic concept behind everything we're studying in this class is now before us. Like we can do sort of anything. We need that not to move. But, you know, aren't both of those arrows pulling down? So how's this thing not going to move? Well, it's not going to move because you look back up at this picture and you say, well, that's a fixed support. So I'm going to call this the force at A in the Y direction. Do you see why I called it that? It's at point A, it's in the Y direction. And a fixed support has that, like that's going to resist vertical motion. And so since those other two are pushing down, I'm sort of seeing that that fixed support better push up or this thing is going to move. So you got to add that error yourself. And we're going to figure out what that is. And the 6 is going straight down, but the 4 is pulling to the right. So does it make sense? There's going to have to be a pull back to the left. So I'm going to call that the force of A in the X direction. And can you also tell both of these are going to try to get that thing to rotate clockwise? So isn't this support also going to provide, I'm going to call this the moment at A. Because that's a fixed support, the only way this thing is not moving is if this support, this fixed support can provide those three forces, can add those three arrows to this diagram, if you will. Are you tracking with that? So now this free body diagram is actually complete. And this is what's important about engineering. In other words, you've got to be the one that attaches this thing to the wall. You're the one that chooses how many bolts go there. I just gave an A-frame to an engineer the other day, and I'll show you what we were doing. And you tell me where what we are talking about right here came into play. So A-frames go all the way down to the ground. And so this is kind of the house. I'm going to erase this. But does it make sense if you put snow on the roof of this thing, that whole system wants to go and just flatten out? So how did I keep that from happening? Well, I put a board across here. But do you understand, like, how do you attach those? What the engineer that's getting paid money to do is spec out what size bolts, how many bolts and what size bolts do you need to put there so that that won't snap the board in half, you know, or rip the wood apart or whatever at the bottom. Like that's what you're going to get paid to do if you continue toward engineering. Now, in my case, I could say, oh, I don't know, just like a whole bunch of them, and that might be fine. Put a whole bunch of bolts in there, and that might be great. But your job as an engineer is to make sure, and then also to not put more than are necessary, because that does cost people money. I don't know the answer to that question. So I drew the plans for this, and I think I got paid like $1,300. The engineer got paid $1,500 for making these calculations. He got paid way more than I got paid because he's doing kind of the really important smart work. That's why you're studying this. So the point is, there is something there, and we've got to make sure it's the case. And so what you're going to be doing in all your problems in chapter 5 is adding, based on the support you see, based on the type of support you see, you're going to add the arrows. So this was adding 3 elements, right? From that previous drawing we looked at. So your job is to say, that's a fixed support. Notice in this case, there's nothing there showing it's connected, but they're telling us, hey, that's got 3 unknowns. And, you know, they show us a diagram right here. It's going to provide Y support, X support, and moment support. That's all 3 of them. If it's fixed, it's going to stop all 3 of those. And so you got to add all those 3 arrows yourself. Doesn't actually matter which way you draw those arrows. If you get them wrong, then you'll get a negative number. It's a good practice to do what they did here. What did they do here? Well, up is positive, so they drew it up. Right is positive, they drew it right. And counterclockwise rotation is positive. In other words, they just drew them all positive. And then if you do the math and they come out negative, then you just know they're the other direction. In my case, because I stared at this shape, does it make sense? I just kind of figured out which direction they must be going. I know I have these drawn the right direction because I can see what the other ones are doing to the figure. Did I obey all the conventions that they just showed? No, I did not. Force of AY is up, that's positive, but then I pulled X left because I can tell that's what's going to happen. It's going to have to pull back to the left. So I'm going to get a positive answer to the force of AX because I know I drew it in the right direction. Okay, well, let's dive into this. This is not hard. What do you think we should start with? The sum of the moments, the sum of the forces in Y, or the sum of the forces in X? Or does it not matter?
I don't think it really matters, does it?
Doesn't matter. It could be that one of those equations is one equation and one unknown. And if there is, then that's the one I'll wish I had done first. But in the end, we got to write them all out. So don't spend any time. Let's just do them in order. So let's see, what are the sum of the forces in X? It's a good idea to kind of highlight that somehow and then just start doing it. Well, my picture shows force of AX going left, so I'm going to call that negative. And then 6 kilonewtons is going down. That's not left at all. And then that 4 is going to the right. So that would be plus 4. And again, I'm noting to myself, hey, all those forces are in kilonewtons. Hey, all of those lengths are in meters. So my forces are in kilonewtons. But I got to modify it, right? So it's at a 30-degree angle. So wouldn't that be cosine? So I got to modify that by the cosine of 30 degrees. And that's it. Those are the only horizontal forces. And so I'm very happy with this equation because it's only got one unknown in it. So awesome. I'm going to finish it, figure out what it is. And notice if I add force of AX to the other side, I'm going to get force of AX to be a positive number. I get about 3.46 kilonewtons for that. I got a positive answer, meaning I drew my arrow the correct direction. Now, again, the thing that's a little weird about this is, if you just read that answer and said 3.46 kilonewtons, you'd say, oh, positive, that's right. Well, you have to look up at my figure to see that, no, actually it's left. So again, that's a bit of a conundrum. It's not a bad idea to kind of do what the book did and just draw force of AX right. Because if I had done that, it would have came up with a negative answer and sort of told us, no, it's actually left. You see what I'm saying? Like there's an argument for not using logic. A better thing would be, to come back in here and label that and say, left or something like that. But the idea here is your job as an engineer is that cantilever beam wants to pull out of the wall with 3.5 kilonewtons. And so you better put enough bolts in so it can't do that. That's the idea. All right, let's keep going. What about the forces in Y? What do I have there? Well, I've got 6 going down. That's easy because I don't have to modify it. I've got that 4 kilonewtons also going down. But it's modified by the fact that it's the sine of 30. And then I've got force of AY going up. There's all of my forces in Y. And again, I'm happy to see, hey, cool, there's only one equation, one unknown. So if I add 6 and I add 4 sine of 30 to the other side, I get 8 kilonewtons exactly for the force of A in the Y direction. Now, take a look at just 2 things. Does it make sense that when you think about putting a screw into the wall, does it make sense the threads of the screw could pull out from the wall because the threads are in wood and the wood the threads just tear through the wood? And so that's what the force of AX is going to do. What's the force of AY going to do? Does it make sense? It's like you got your screw pushed into the wall and there's too much force on it. What's going to happen to that screw if you push up or you push down? What's going to happen to the screw? It's not going to come out of the wall. What's it going to do?
It will snap.
It'll snap. It'll what's called shear. It'll just snap in half and the bolt will be left in the wall and the other one will be up here. It'll just shear into two pieces. It's like cutting it with scissors. That's what shear is. So can you see that, well, 8 kilonewtons, if you put one screw there, could snap in half. Is one enough? Well, maybe it is if it's big enough. What about 2? What about 4? What size should I pick them? Does that make sense? Like you've got to resist 8 kilonewtons of shear force. So there's 2 very different things happening there. One of them is pulling out of the wall. The other one is just ripping in half. And so, in a sense, good choices. Well, let's keep going. What about moment? And I might want to say here, the moment's around A. Does it make sense that's the natural point to move this around? However, I would like you to understand that no matter what point you pick, the sum of the moments needs to be 0. If you want to pick some other point, you can. However, the fixed support is only going to show a moment around A. This is a little trickier, so let's go do something ahead of time over here. I'm looking at this little extension right there that's 1.5 long. And I'm also told that this is 30 degrees. So if I do this, let's see, the sine of 30 degrees times 1.5, this ends up 0.75. Perhaps you remember your nerd math from Math 112, 30, 60, 90 triangles. That side will be half the size of the hypotenuse. And then if I do Pythagorean theorem on 0.75 and 1.5, I get about 1.3, I think. Is that right? 1.5. Just double checking. I'm just going to do 1.5. 1.5 cosine of 30. Yeah, 1.299. So I'll just call it 1.3, close enough. So let's think about that when we get down here, because remember this force up here has a horizontal component, but it also has a vertical component. Maybe it'd be better if I drew it down here. So I've got to consider both of those forces. So the moment as a result of that 4 is more complicated. So let's take care of the easy one first. Well, 6 is trying to get it to rotate this way, and it's perpendicular to that 1.5. So I'm gonna have to modify that, and that's causing negative rotation. So it'd be 6 kilonewtons times 1.5 meters, and that's gonna be a negative rotation. So that's sending it clockwise. This vertical component of 4 over here, which we figured out a while ago, that 4 times the sine of 30 number a minute ago. I think I'm going to write that down just somewhere else so it looks cleaner. 4 sine of 30. This is 2. And 4 cosine of 30 is 3.46. So those are the 2 forces up there. This is the 3.46, and this one is 2. So that 6 is pushing down, but then isn't the 2 also pushing down? And what's its distance though? How far is 2 away perpendicularly from A? Notice you got to think harder about that. Well, isn't it this 1.5 plus this 1.5 plus this distance, which I just calculated right there. So it's actually 3 And 1.3, 4.3, that's how far away that force is perpendicularly. You agree with that? And that's also negative. But notice the 3.46 is also at a distance. If I think of it as a straight line, it's at this distance right here from A. And that's that 0.75 I calculated earlier. That's exactly how far above this horizontal bar that force is actually going. So, and what direction is that causing? Since it's really kind of over here, is that positive or negative rotation that's causing around A?
Negative because it's going clockwise.
Exactly, it's going clockwise, so it's negative. So it's another negative. So it's a force of 3.46 times the distance of 0.75. Notice every single thing that's happening there, as we said earlier, wants this very badly to rotate counterclockwise. I'm sorry, clockwise. And it's in previous sections, we just said, okay, that's how bad it wants to rotate. We're done. But that's not what you do as an engineer. Like, you got to stop it. So your job is going to be then to go back and, well, figure out what this moment of A is. And then notice the moment of A is just moment of A, like, and it's going the other direction. So I can just say plus the moment of A has to be 0. So crunch all those numbers. Moment around A, work this out earlier, is, what would the units be? I've been lazy about units here. It's 20.2, but what are the units? What have we been multiplying?
Kilonewtons times meters.
Yeah, we've been multiplying our forces in kilonewtons and our distances in meters. So this would be kilonewton meters. So basically, these three forces that we just answered, basically, if you want this system to stay static, then you better darn well make sure that fixed support can handle all three of those forces. We won't belabor this point, but I'd like you just to think about it for a second. If this is the wall, and by the way, this is a lot of the way engineers kind of show that, and I'm going to put a little plate over here on this wall, and I'm going to bolt the plate in there, and I'm going to bolt it in here. Awesome. And so then it goes out there, and we'll just say it goes from there. This is also something engineers do. They draw a little split, meaning, yeah, okay, great, that's out there somewhere. You tell me what's going to happen. If there's a whole bunch of force acting down on this right here, trying to get this thing to rotate, which bolt is more important over there in the wall, the top one, the bottom one, or does it not matter?
The top one, because the bottom can't physically go into the wall, and that's where it's going to be pushed.
That's exactly right. Notice, as far as the force going up and down the wall, it doesn't matter where the bolts are. They're just in the wall. Great, awesome, won't move up and down. When you try to pull this thing out of the wall, it doesn't matter where the bolts are. They're just in the wall. Awesome. But when you rotate it, that top bolt is more important than the bottom one. Can you picture that? In other words, if it is going to rotate out, what Daniel said was exactly right on. Isn't it going to do this? Isn't it going to look like this if it rotates out? Isn't that what's going to happen? So the top one's going to get ripped out of the wall. So the top bolt needs to be longer, maybe, for instance, to not rip out of the wall. If the top one was really long, that would be good. If the threads were huge or something like this, like, it's got to grab the wall really well. So as far as rotation is concerned, we don't even really need a bolt in the bottom. We just need them in the top. So maybe we put 4 bolts in the top and 1 in the bottom or something like that. That could make the difference in this working or not. Like, maybe as an engineer, you could locate them in the right spot. Instead of needing 6 bolts, you only need 4, 1 in the bottom, 3 in the top, instead of 3 in the top, 3 in the bottom. So, you know, we just found these 3 numbers, 3.46, 8, and 20.2. But now you're going to proceed to make sure that fixed support is actually supported in that way. And again, I'm talking about, bolts into wood, but it's like this could be welding too. You could weld it to it. I don't know how much force welds can resist. I mean, there are different qualities of welds. But the fact that you found these what engineers call reactions, you see why that's kind of a good name for this? If you came over here and you applied this 4 kilonewton force and this 6 Newton force, then what is the reaction at the wall? What's happening over there as a result of that? Well, that's what these 3 numbers we calculated are. They're the reactions. And so we got to do something about that.
I'm kind of curious, actually. When it comes to actually putting like a relatively large bolt in a wall,
Mm-hmm.
How does that actually work? Do you just like, I guess with wood you could kind of drill it in with a pilot hole, but how would you actually get a thread for like another material, like concrete or something?
Yeah, it's an interesting question. So they make actually concrete specific bolts, and it is very important to drill the pilot hole the right size. Generally speaking, what you need is the pilot hole to be big enough to let the shaft of the screw go in, slide in, but the threads have to carve their way into the concrete, basically. The cool thing about it is if the front edges of that threaded bolt are carbide or really strong, they sort of blaze the trail, and then the stuff behind them has less trouble getting through it, if you will. But yeah, they're actually concrete specific bolts. I've bolted some stuff on the foundation of my own house using those, and I was like, God, I can't believe those go right into concrete. It's amazing. But you can't drill the pilot hole too big. That's not good. And if you drill it too small, it won't go in. So, and of course, then there's the steel version, and then you may even have to thread it. Like you put a threaded insert into the wall, like you actually drill a big hole, and then you glue effectively a nut into the wall, a giant one, into the wall, and then you just run a regular machine screw into it. So, but there's all kinds of ways things can be connected. But I think wood just is kind of a neat one to think about because you can picture it failing in your mind a little bit easier. So you see, we're not really doing anything new here. We're just going one step further and saying, okay, well, what's this? We now know what the wall's going to have to be capable of doing in order for, this whole thing to actually stay static. Well, let's take a look at, let's see, how much time do we have? Yeah, we got to do that one. Let's do that one. Stare at this one for a second. So this is in your book. It's question 12, but it's one of those ones that you don't have answered. So notice it's kind of simple in the sense that there's just one force on it. But what do you notice about those supports? What's this one?
That a roller one?
Yeah, what's that rollerish one? It's a rocker because it can pivot. It's not rolling, it's not a ball, so it's a rocker, not a roller. But yeah, you're seeing it correctly. What's this one over here called? That's a pin. So you've got to add the force arrows to this. So there's only one force, 4 kilonewtons. But that's not good. Like this whole thing's moving. You've got to be able to come back and say, oh, rocker, oh, pin. What do pins do? I'm going to follow the conventions this time and just say, well, right is positive, so I'm going to call that the force of A in X, and up is positive, so I'm going to call that the force of A in Y. Pins only can provide support vertically and horizontally, but they allow rotation. Can you picture that if you put a force underneath here, in this particular example, that thing would just lift up in the air? There's nothing stopping that, right? So pins do not provide moment, so there's no moment added to this. What about that rocker? How many forces can a rocker provide? By the way, you see this word smooth. What does smooth mean? Why are they saying smooth? Why don't they just say a pin? What's dumb? What does smooth mean? That's like code for something that's come up in your book a little bit here and there.
It's easy to rotate.
Yeah, it actually means it rotates frictionlessly.
Frictionless. Okay.
So it's
Yeah.
without friction, because you might picture if you actually put a bolt there and clamped it down, that thing is not just going to move easily. Like it is going to resist rotation a little bit just because of the friction. So they're saying it's smooth, meaning it's not going to help at all, because you're going to get nothing in rotational support. So that's what smooth is code for. So let's see, rocker. Oh yeah, rocker. Reaction is a force which acts perpendicular to the surface at the point of contact. Only perpendicular. Again, I don't think that's obvious. It doesn't feel obvious to me. In other words, you might come over here and say, you know, where are you going to put that force? Well, that force is right there, perpendicular. So I'll just call that the force at B. Now, can you break that yourself based on we're told that it's 30 degrees? Can you break that into its X and Y components? Yes, and you need to, because we can't work with stuff at angles. We got to convert it. So now you've added everything that needs to be added. I'm going to go back and take these arrows away because they make it look like they're forces. I'll just leave the names up there. So now I've got 1, 2, 3, 4 arrows, and collectively those have to make sure that thing doesn't move up and down, the thing doesn't move right and left, and the thing does not rotate. So again, let's just sort of mindlessly go in order. And again, notice they told us the pin at A and the rocker at B, they told us what those were. But let's just go find the sum of the forces in X again. Make sure they're equal to 0. Let's see, what do I have in X? Well, that force of AX is going to the right. So I guess that's in there. That's going to the right. And then I've got this force of B over here. Let's see, I got to draw this out. I'm going to screw this up. So I guess if it came shooting in from that direction, and the X version would be shooting in that direction. I want to show you something kind of cool here. Like what you don't want to do, this is what you don't want to do. Call this the force of B in Y and the force of B in X. The reason you don't want to do that is you just created too many unknowns. It's way better. It'll save you trouble later. I don't know. It's definitely possible, but it'd be better if we just called both of these the force of B, except modified them. So let's see, if the 30-degree angle is up there, where's the 30 go here? I think it's here. I think that's the 30. So this would be force of B modified by the cosine of 30 degrees. And this other one would be force of B modified by the sine of 30 degrees, I think. So then I can say, oh, look, in the X direction, that's minus force of B modified by the sine of 30. That's it, and that equals 0. I'm not happy at all this time, because that's got 2 unknowns in it. So that doesn't mean the equation's bad, but I can't do anything with it right now. So I'm basically hoping, force of AX, force of B. I'm sure hoping that there's some other equation that's got all those in it, because that isn't working too good. So, okay, save that for later, fine. What about the forces in the Y direction? That was the world's worst sigma that I just drew. So force of AY is going up That's up. Cool. 4 is going down. That's cool. And then that force of B cosine of 30 is going up. Am I happy with that one? Not happy that there's 2 unknowns here. Not happy there's 2 unknowns here. Oh, cool. I got 2 equations, 2 unknowns. Well, no, I don't. I don't have 2 equations, 2 unknowns. Do you see that? There's 2 equations and 3 unknowns. I'm not happy at all. This is not good. Progress. Perhaps the sum of the moments. The sum of the moments around what? Notice it's not obvious this time. Should I go around A or should I go around B? Or does it not matter? What do you guys think?
Would we maybe have to go around both and do them each separately?
Yeah, maybe. I don't know. I'm just going to try one. Maybe we'll do both. I'm just going to pick, I don't know, B over there looks confusing. There's like arrows going every which direction. So for that reason, I'm going to go around B. Do you understand why? I'm going to go around B. That's because all those forces won't contribute. Does that make sense? They're all pointing right at B, so they're not going to contribute. Okay, around B, fine. Well, notice force of AX is pointing right at B. Therefore, there's no distance for that one. It's not above it. It's pointing right at it. So force of AX is not going to cause any rotation. But the force of AY will. And it is clearly at a distance of 8, 6, and 2. Do I have the sign right? Is that a positive or negative around B? It's causing this rotation, isn't it? Ah, that's clockwise. That should be negative, right? And then I got 4. I got a force of 4. It's going to cause rotation in this direction, which, because that's counterclockwise, we call positive. So that'd be a plus. 4 times the distance of 2. Again, I'm thinking in my head meters and kilonewtons. I'm just not writing it down. What else? Well, again, do you agree all these other forces are pointing right at B? The force of B by itself is pointing right at B. And so that's it. That's it. So awesome. I am happy because that's only got one unknown in it. Force of AY. Sweet. So that means force of AY is just 1 if I solve it. So there's my first answer. Force of A in the Y direction is 1. And because that's a force and all of our forces are measured in kilonewtons, I have that answer. Now you should see this as, if you will, kind of a house of cards, like, oh, cool. Now what can I do? Well, now couldn't I put that back in? Let's see, what color should I use? Red. Couldn't I put that in back up here now? And that equation that was 2 equations, 2 unknowns just has 1 equation, 1 unknown. So I could say 1 minus 4 plus force of B cosine of 30 equals 0. That's going to allow me to find the force at B. When I do that, I get 3.46. kilonewtons. And then I noticed the same exact thing. I think, hey, there's that first equation up there, and it had a force of B in it. So if I go up there and stick 3.46 into that, then I should be able to find the last unknown, force of AX. And so it sort of turned out in this case that it would have been better had I done the moments first. And I don't know, did I guess lucky and do the moments around B? I guess right. I guess then it wouldn't have worked so good if I went around A. I'm gonna let you think about that for a minute. So that means the force of AX minus the force of B, which is 3.46 times the sine of 30 has to be 0. So the force of A in the X direction, I got a positive number again. I got 1.73. Again, the fact that I got positive answers means, well, I guess you could say I got lucky, like all my arrows were actually pointing in the right direction. Now, if you stare at this figure, just to grow your awareness, like if force B is over here pushing this direction, isn't that going to try to slide the beam left? Therefore, isn't A going to have to push back to the right? So it makes sense that that would have to push back to the right. If force 4 is pushing down on these, then aren't force B and force AY, aren't those going to have to both push back? Anybody answer this question? How come it's not 2 and 2? Like, isn't 4 pushing down, and so wouldn't they both be 2? How come they're not 2?
Well, the 4 kilonewtons is more over to the right side, so
Yeah,
of course the forces, so that shouldn't affect that. But
yeah, it's closer over there, so it's gonna have to work harder. I'm doing this all the time when I'm designing houses. Like, here's a beam, and here's a post, and here's a post. And if right in the middle, this beam weighed 1,000 pounds, then this post would have 500 and that would have 500. But if that weight up there was over here, then maybe it's not 500 and 500 now because it's closer to that side. Maybe this one is 700 and that was 300. Notice they still total 1,000. They still have to push up for a total of 1,000 to keep this whole thing from going down. But maybe the one on the right has to work a little bit harder. So grow your intuition and see that that kind of makes sense. I don't know. I'm just kind of curious. I think we should just quickly say, well, what if I had done this around A? I wonder what would have happened. Let's try that really quick. What's the sum? We sort of don't need to, but let's just see what happens. What if I had done the sum of the moments around A? What would have happened had I done that? So the sum of the moments around A, the 4 would have been pushing, but then this time the 4 would have been causing negative rotation. So I would have had a force of 4 times the distance of, it's too small for me to see now, 6 and 2. So 4 times 6. So notice that 4 around the other point is at a distance of 6. And so that's great. And then the force in the X direction here, whoa, that was a bad choice. The force in the X direction here is pointing right at A. So the force, this isn't going to do any good, but this force of B cosine of 30, that's at a distance. And that's causing rotation to go the other direction. That's positive. So that'd be the force of B cosine of 30 times the distance of 8. So plus force B cosine of 30 times the distance of 8. And that's it. Notice that is kind of a totally different equation. So let's see, 4 times 6 is 24. So if I add 24 to the other side, and then I divide by 8, and then I divide by the cosine of 30, I get force of B is 3.46 kilonewtons. Hey, same answer I got before. Doesn't matter. That's the answer. I didn't get lucky and guess the right one. Doesn't matter. You may have, maybe you heard Ben, but Ben said maybe we should do both. I think it was Ben that said that. In other words, I said, should we do it around B or around A? And he said maybe both. Notice if we had done the moment around A and the moment around B, we would have gotten that answer for force of A, and we would have got this answer. We would have got both of those, like just from the moment calculations, if you will. And then maybe that would have saved us some time with the other ones. I don't know. But doesn't make any difference. But I will say this, if you have to pick, doing the moments first is often a good choice. Like that will regularly be the one that does not have two equations, two unknowns in it. So that's worth thinking about, I think. All right, I think we got time for one more. Let's see, which one shall we do? Shall we do this one? Yeah, that one looks good. Let's do that one. This is a good reminder. Determining the tension in the cable and the horizontal and vertical components of reaction at pin A. So that's a really weird drawing. Notice that, what is that? Like, would that do any work? Like, that seems like a really contrived thing. I just can't imagine somebody making that. That doesn't really make any sense. I could imagine it if they took this up here, threw that over here, and then came over to like a winch. That way they could actually lift that weight up and down. I could see that doing something. So this is really weird. I think they're just having us practice. This is strange. Why would you have these two cables up here? Why would they go around? Why would they go around a pulley? You know, see what I'm saying? That's just kind of an unusual thing to do. So again, they told us a pin at A. Well, again, I'm going to use the same conventions and say, okay, well, if that's true, pins provide a vertical force, which I'm going to use the convention of up is positive. And force of A in the X direction. Right, it's also positive. So I'm just picking them both to be positive. So there, I added extra arrows. Would you agree that this is up and that is up? This is the concept of a free body diagram. In a sense, this might be a place where maybe I shouldn't be so lazy. So let me show you what I mean by that. I'm on the lazy side, but I really probably should draw a free body diagram, because there's more than one connection. There's also that connection up there at D. But my free body diagram is really just this beam here. And it has a force pushing up here. I'll call that force 1. And another force pushing up here, I'll call that force 2. And another force pulling down here, I'll call that force 3. And then it's got force of A in the X direction and force of A in the Y direction. It's actually got all 5 of those forces acting on it. That's the idea behind a free body diagram. Does this pipe AC, does it care that there's a pulley up there? No, it doesn't know. It knows it's being pulled and pushed on in those 5 ways. Do you agree with that? Now, there's one thing wrong with my free body diagrams. Anybody know what it is? And I don't mean the lazy stuff, like I didn't put the links in. I should add those. I should put the 5, 3, and 3 in there. And the angle, like that force 2 is going off at an angle. I should add that stuff too. But what's wrong with this picture? That anybody know?
Is FAX pointing in the wrong direction?
It might be, but remember that'll take care of itself. If I get a negative number, then I got it wrong. It's worse. It's a little worse than that. What's true about how cables behave? If this turned out to be, say, 50 pounds or whatever, what's the other one going to be?
Had to be 50 as well.
It's also 50. That's what cables do. Does that make sense? Ropes and cables, they're going to equalize the tension. So you can't have one of those pulling at 50 and the other one pulling at 80. Cables won't let that happen. Does that make sense? So how should my diagram be drawn? Because remember, I'm down here with how many unknowns? Well, I haven't really read the question yet, but there's 5 of them. Well, I shouldn't have 5 of them because of what we just talked about. I should call this force 1. Hey, good. I'm not have so many unknowns now. Does that make sense? And I guess I'll call this force 2 since. And now let's just keep going. Like, do I actually know anything? I haven't really read the question. Determine the tension, reaction at pin A, pulley D is frictionless. Why are they telling us pulley D is frictionless? Well, that's because those two forces would be the same. If there was friction, then they could be 50 and 60, but they're frictionless. So it's going to equalize. And the cylinder weighs 80 pounds. Okay, cool. That means I don't even need this force 2 down here, do I? I could just call that 80. And don't forget this note here. If the beam's weight's in kilograms multiplied by 9.81, we had to do that earlier. But in our case, it was pounds, and so we don't have to multiply by anything. So I really only have 4 unknowns. I thought I had 5. I'm sorry, 3. I thought I had 5, but I only have 3. And I added the beam weighs 42 pounds, so I'm missing an arrow. And notice I added that myself. Where does that 42 go? Where?
In the center of mass for the beam.
Right in the center. Assuming it's the same beam all the way through, which they typically are, it'd be right in the middle. Cool. I have everything I need. I have a free body diagram. Do you see why it's called a free body diagram? Because it's just floating in space. That's the way you have to look at every member of a truss or anything that you see. It's floating in space. It has a bunch of arrows pushing and pulling on it. And the sum total of all that is, it better be static. It better not move. Can't rotate, can't move up, can't move down, can't move right, can't move left. So now we weigh it in. I would really like to not have lots of equations, lots of unknowns. And so true to the point that I made earlier, it maybe would be a good idea to start, I got to speed up here a little bit, with moment this time. Why is it a really good idea to pick the moment to be around A as opposed to around B or C? Why is going around A an excellent idea?
Because we get rid of f of ax and f of y, ay.
That's exactly right. Don't go around some other point so that you have f of ax, f of ay, and f of 1 in it. This will get rid of 2 of my 3 unknowns. You see how brilliant of an idea that is? Like, that's the kind of thing you got to start thinking about a little bit. You can write any equation you want to, and they're all going to be 0. But the question is, can you solve it? This is a great place to start. So let's see, what do I have? Well, I've got force 1 trying to get this thing to rotate in the counterclockwise direction, which is positive. So I've got force 1 times its distance away from A, which is 5. I've also got the other force 1. Let's see. Also trying to rotate it in this direction. So that'd be plus force 1, and it's a distance of 10. What's wrong with what I'm writing right here? What's wrong with what I just wrote?
We have to also multiply by the angle.
Yeah, remember the distance has got to be perpendicular. Is that distance 10 right there perpendicular to that second force 1? No, I've got to modify that to be perpendicular. So that force 1 has got to be modified. By what? Well, I'm told up here what angle that's at. That'd be 1, 2, let's see, this would be the square root of 5. So its vertical component would be 2 over the square root of 5. So I've got to modify that by 2 over the square root of 5. It's really easy when you're doing these calculations to forget that that's just a force. I just modified the force, and now that's a distance of 10. And then 40 is trying to get it to go the other way, negatively. So minus 40, and it's in the middle of the 13-foot beam. So that'd be 6.5. And the 80 also wants it to rotate negatively. And it's a distance of 13. There's all the forces trying to get it to rotate around A, and I need them all to be 0. I'm very happy with that equation because it only has force 1 in it. So this is a very good day. So if I don't screw that up, then I get that force 1 is going to be 94 pounds. That was a great equation to write. Well, let's proceed. I think I'm home free. I sort of don't think it matters what I do now, but I'm just looking, thinking, okay, now these force 1s are sort of 94 pounds over here. I can sort of add those in. And so I see those pulling up, the 40 and 80 pulling down, like all of that is known. And then the force of A is the only other one. So, you know, with respect to the sum of the forces in Y, I can see that I'm going to be able to write an equation with only one unknown. So I'm going to go ahead and write it this way. I've got force of 1 pulling up, straight up, so I don't have to modify it. But then I've got another force of 1, as we said a minute ago, modified by the 2 over the square root of 5, also pulling up. And I'm going to replace those with 94s because I know them. And then I've got 40 going down, and I've got 80 going down. And then I've got force of AY going up. And I need all those to be 0. So if I replace that with 94 and I replace that with 94, then again, very happy. I've only got one unknown. So I solve this and I get I get something that hasn't happened before. I get force of AY equals negative 56.4. 56.4, not 54.6. What does that mean?
It's going the other direction now.
Yeah, just means that it actually wants to go oddly, you know, with all of this weight on it and so forth, strangely, if you will. If that wasn't supported correctly, A is going to go down, not up. Let's see. No, up, not down. Can you see that happening? What? You're saying that if it wasn't strong enough that side over there would actually go up in the air? Yeah, I guess that is what it's saying. I don't know about you, but I didn't think that was obvious to start with. It's got all these forces pulling on it. Seems weird. But remember, it wants to rotate, right? It wants to rotate. So actually it wants to go up. Now, based on the fact that I drew that nice picture up there, aiming it up, then you can just say it's negative and be done. That's okay. Or you could go back and draw it down and rename it positive if you want to. That's fine. Doesn't matter. All right, I got to get you guys out of here. But let's at least quickly write down the sum of the forces in X and make sure those are also in equilibrium. So I got force of AX that wants to go right Oh, look, there's just so much stuff that's not even there. Like the 40 doesn't exist. The 80 doesn't exist. That first force 1 that's straight up doesn't exist. So a ton of stuff doesn't exist. And what this tells me is, hey, if I'd have written that equation first, it would have worked first too. The only thing happening is the kind of the horizontal component of this force over here, which is 94 modified by, I guess that'd be 1 over the square root of 5, wouldn't it? Its horizontal component is 1 over the square root of 5. And it's going left, so I'm going to say minus force 1 modified by 1 over the square root of 5. That's it. That's all the forces that are left and right. That has to be 0. Again, you don't need to write force 1 there. You could have just written 94 in there from the start. And I got force AX being positive, which means I drew it in the right direction at 42 pounds approximately. So notice I have all of what it asked for just kind of naturally. Determine the tension in the cable, 94 pounds. I figured that out. And the horizontal and vertical components of the reaction at pin A, that's because it's a pin, it's only going to have horizontal and vertical reactions. So basically I'm going to have to screw that to the wall in such a way that it isn't allowed to go up by 56 pounds of force, and it isn't allowed to get jammed into the wall. Hey, isn't that interesting? It's getting jammed into the wall. If it's getting jammed into the wall because of this force over here pulling left on it, does it make sense? I really don't need very many screws. Like just a drop of glue would do it, right? 1 screw. Just keep it from falling down. The only screws I need really in the wall are because of that 56. Do you see what I'm saying? So it's really important to understand which way this is going. Do you see what I'm saying? Because it's not trying to rip out of the wall, so I don't have to think about, how firmly attached are those screw threads and so forth. It's like, no problem. I just got to make sure the wall's made out of concrete or something that it doesn't just smash through the wall because it's made out of sheetrock or something like that. So it's very important to know which direction these are going. You agree with that? You see that? My guess is you could do a good chunk of the chapter 5 assignment if you want to use your time really wisely. You'd be best off to go try a bunch of stuff in chapter 5. What I'm going to show you on Thursday is just some more examples, and then I've got a kind of a demonstration that I usually do. I'm not sure how I'm going to do it because I don't have access to all my stuff at school, but I could just take the numbers. I could describe it to you and not. The demonstration I did in class actually had the students all come up and take all the measurements, and we made a very realistic problem, if you will, that's kind of like this, and where we took all our own measurements and we weighed the beam itself and found out how much it weighed and all of that, instead of just having these arrows pointing at things. So we'll probably do that next time, but I'll just tell you what they are and kind of set the scene and help you understand what we did and so forth. It's kind of like this one where it's, like a beam attached to the wall with cables holding it up. I got a piece of string coming down from the wall, so forth, holding it up. And then I actually put a spring scale in it from the physics department, and we tried to calculate what it would read, and it worked. It was cool, just to see.
Oh, wow. That's cool.
It's kind of cool to see. It's like, wow, this stuff actually works, All right. Get yourself out of here, or stay after and ask a question or two.
So I have actually a question about this problem because it's still like not clicking in my head about the force AY, because we got a negative number, so we need to change the direction of the force on our free body diagram. Is that what it is?
Yeah, I mean, you don't have to change anything, but it's just my instinct was, if I see this attachment sitting on the wall like this, there's my beam, just because of gravity, don't you find yourself thinking, hey, that's going to go down, like it's going to fall. Everything falls toward the earth. It's going to go down. And so So therefore, to stop that from happening, my drawing here is perfect. Like I'll push back up and make sure it doesn't fall.
Mhm.
Great. But then we got down and we got a negative number. Huh?
I think that's because of the cables, right? Because it's attached and it allows it to like twist.
That's
And we have a weight pulling on other side and it like basically pulls it up.
That's exactly what it's doing. In other words, if you look right here and you say, wow, look at that 80 pounds, that's really big. That's
Mhm.
pulling down really hard. But notice because of the cable being attached right here, does it make sense if this pulls down and the cable's attached here, then it's actually making the top of this one to rotate up? Because that's the biggest weight up here. Well, 94 is big too, but it's kind
That's
of,
because it holds all of the weight of
yeah,
the beam, whatever.
that's right. It's more like holding the beam from falling down, but this 80 pulling down is really causing this beam to try to rotate around in this direction like a propeller. So despite common sense, actually this wants to go up with all this weight on it. And so I would have thought force A would be pushing up to resist the pull down, but it turns out force A is actually going to have to push down on this to keep it from flying up in the air.
Mhm.
So there's absolutely nothing wrong with just what we did. It's just that it's important to know that as a result, wow, that wants to go up. I never would have thought. You can't always just look at it and see. It isn't always obvious. It was obvious in all the other problems we did, but it wasn't obvious in this one. Although in hindsight, I think you can look at it and go, oh yeah, I guess actually that would do that, wouldn't it?
Okay.
If you, one other super quick thing, but remember we were talking about that beam out at your house,
Mhm.
and here was the bank. And so we want happy people to be standing out here. And so because that's a deck, we might want to support this right here, up above the ground, because you don't want the wood touching the ground. And so, your first look at that and you think, okay, great. Yeah, this beam has weight, but because this thing is supported, across here, does it make sense that end actually wants to go up? So like we can't just set it on top of a block right here. We can't just set it there. We're gonna have to like anchor it to it. We're gonna have to put some straps up the side with some bolts in them, because that actually is gonna want to go up, not down. So the problem we just did is really similar to that. You see what I mean?
Yeah.
So that's kind of why it's so important to, write all of these things out, because if you don't make all these calculations. And so one of the things I see that I need to show you guys some of the stuff I do on the side, but sometimes when there's a truss there, there'll be uplift on that truss. In other words, that outside end, the truss will actually want to go up, not down. And so you can't just set the truss on there and put like one little nail in it. Most forces on a roof are downward. And so the important thing is just to have it sitting on a wall and a little toenail and you're fine. But if it wants to lift up, now all of a sudden you got to put some kind of a strap over the top of it. And
Yeah. And you having a meeting today, right, with John?
yes.
Okay. Because I really like to participate. I mean, be there, but I do have a class like at 1 o'clock. I want to try to, because it's like not really that important class. So I want to ask her if I can stay in the class for like 30 minutes, 20 minutes, and after leave.
Yeah,
Is
there's no reason to send me a text if you're free, and I'll just zoom you in to our discussion.
Sure, but I really like to have a face-to-face.
Yeah.
So I'm gonna try to work that out.
Okay, great. All the better.
And did you check? You probably didn't open the homework and the project I sent you.
Not yet. I was going to do that next, actually.
Okay.
Do we need to talk about that?
So maybe because what I did from all of the forces on the actual wall, I just brought them all down to the concrete pad, like where's the foot and toe.
Mm-hmm.
I brought it all the way down, so it's going to be super easy to just like how you see the distance right away.
Good job.
I mean, I marked it there on the paper.
That sounds clear. Sounds totally clear.
And
And
do you
mine-
know what is the answer for it?
Not for sure. Because when I was doing it with you guys, one of the things I wasn't sure what I did last time is like I had the post here and there was all this weight on top of it, kind of coming in over here.
Mhm.
So the question is, where is that weight? Is it on the outside edge? Is it on the inside edge? Is it on the middle? And I might have made a different decision when I was talking to you guys than I did last time I was there. Um,
I mean, me and Ben, we talk about like the floorboard,
uh-huh.
but the beam, and usually, you know, it bends on the inside, basically does that. So on the wall, it actually should be on the inside corner, but we actually just capped it as your example.
And I would have marked that right. Realistically, it's such a small difference because the wall's only 8 inches wide. It probably doesn't make a gigantic difference. What you just said is absolutely brilliant because it is going to bow down and therefore it will actually be touching on the inside, not the outside. So that is a brilliant observation on your part. I love it.
Yeah, so probably just answer should be a little bit different, a little bit, not a lot, but a little bit. And it's still recording.
That's right.
Yeah.
We got nothing to hide.